So what I'll tell you about here is what we're doing to work with fluidics inside a transmission electron microscope. So I'm professor at the at Nanolab. It's a facility here at the Technical University in Denmark, and I'm working with quite a number of people around the world that I'll show you here out in the slides. But overall, what we're trying to do is to try to help scientists studying complex nanoscale processes under dynamic conditions such as liquids or gases. And typically, if you're a material scientist, what you'll do is that you'll end up trying to use all kinds of different methods to see what's going on, because you can't see it directly, and then somehow reconcile all these measurements into one complete understanding of what it was that was actually going on. Now, the in situ microscopy we've been talking about today, of course, hopes to combine all these methods, give us this amazing atomic scale spatial resolution, but also now, you can get frame rates up to 1 kilohertz if you want, and you can do spectroscopy, while at the same time let in reagents that can do chemistry, and also apply heat or pressure or biasing of magnetic fields to really observe all types of processes in liquids and gases. So maybe would this be the method, one method to seal it all here? But of course, we got to get electrons in there. So one way of seeing into liquids, you could use a scanning or a transmission electron beam. You could look at the electrons coming back out from your sample if you have a liquid encapsulator under an electron transparent membrane, but it doesn't give you very good resolution. So people typically opt to go for a transmission electron microscope shooting electrons through it. And this has been done for many, many years. Back even in 1944, people were trying to put liquids into a TEM and got really low resolution, and all started just using, optical microscopes because they were better. But then in 2003, Frances Ross built a chip-based system at IBM with ultra-thin silicon nitride membranes, where she could squeeze a thin liquid layer in between and even have electrodes in there, and then begin to study things with what would then be reasonable resolution, better than optical. And 10 years later, this is 70 years after the first liquid was in a TEM, a bunch of science papers came out, both in nitride-based systems, but also using graphene liquid cells, showing that now you can get atomic resolution in liquids and begin to really understand a lot of phenomena going on. So this is this new area of liquid phase electron microscopy that's being developed in recent years. But it's kind of fun, I think, to see that it's actually been going on for 70 years. And my group, you can say that we're making microchips for microscopy, and we are really nicely based here at the Technical University in Denmark and our clean room facility. We got an amazing clean room, and the students can get access to it and be trained to become clean room engineers if they want that. We're currently building a new big add-on to it because it's completely filled with people and companies, so we need more space. It's a hideously expensive expansion, but we're really looking forward to it. And then also in our center, we have a really nice nano characterization facility with a wide range of electron microscopes. And also right now we got a new Spectra Ultra. And if you're not a TM person, this looks like a box. But to us, this is an amazing new tool with unprecedented resolution and spectral capabilities. And we're even getting another one at DTU Physics. So we're really well equipped with electron microscopy. So basically you can see here we got amazing facilities for creating and seeing the smallest structures. And now, if we want to make chips for liquids, then one thing we can do is, of course, to take two chips with ultra-thin membranes and just squeeze them together. And this is what people typically have been doing, and you can buy chips from different companies and holders to put into the TEMs. But they have this drawback that there's a vacuum in the TEM, and the membrane to encapsulate the liquid will then start bulging out because of the pressure of the liquid. And that gives you fairly thick layers of liquid and pretty poor resolution. Also, in most of the systems, you have pretty poor flow, and you can get electrochemical electrodes in there. You can also get some temperature heating and so on. So they're kind of nice, but they're also quite tricky to use. Then if you want better resolution, a lot of people opt for this graphene blister cell design where you trap ultra small liquid droplets between two layers of graphene. This gives you ultimate resolution. The encapsulation is just one layer of atoms ideally, but you have no flow, no electrodes, you don't know what pressure is in there, and it's probably incredibly high. And also really not much control of, what chemistry is going on in there. And it's do-it-yourself and pretty irreproducible, but you can begin now to buy robots that can fabricate it. So maybe it'll be more reproducible. In our lab, for many years, we worked on trying to find a good solution between these two. So we made these suspended nanochannel systems, where we have nice nanofluidic systems suspended on a silicon nitride membrane. So here we can have huge, nice control of flow. We have well-controlled liquid layer thickness. And also now we're making systems with temperature control, and we're just starting up a PhD project to create electrodes in there. So this is beginning. We think this is a really nice system for getting controlled views of things in liquids. And if we take one of these chips, typically the height we're making the channels can be something between 20 nanometers to 3 micrometers. In TM, you probably want about 100 nanometers. The nitride thickness can be, right now we made them down to about 10 nanometers. And if you put pressure on them, well, a 100 nanometer channel will bulge about 10 nanometers. So the bulging here is really not something you want to be concerned about. And they can take a higher pressure. We pressurize them to 12 bar without problems. And to get flow in there, we made 4 inlets and outlets on the chip, and between these we connected some bypass microchannels that give you high flow rates, so you can make fast exchange of liquids, and then they're connected with a nanochannel system that's then suspended on a membrane in the middle of the chip. And if you put liquid into one of these, then you'll see air-filled channels being filled quickly. The capillary pressure in these nanochannels are extremely high. So there's a minus 10 bar capillary pressure very often, and it just sucks in water very fast. You can zoom in on the water in the TEM. It's got nice contrast compared to the membrane surrounding it. And then if you fill in, say, some gold-containing precursor and irradiate it, you can precipitate out gold crystals by the electron beam. And if you start zooming more into that, this is something done by David and Ude in Ulm, for instance, but you can get that in many TMs. You can get atomic resolution, typically angstrom resolution in liquids while looking at gold in it. So this is giving you much better resolution than the commercially available systems today, and something approaching that what you find in graphene liquid cells, but now with flow control. And we got nice flow control. You can even now begin to see fun nanofluidic phenomena. Here we're injecting water, which is the dark liquid, into hexane, which is the less dense and lighter liquid. I mean, this is something we only had time to do very recently, but just imagine all the things you can begin to do of microfluidic experiments with mixing, droplet formation, all kinds of interfacial processes going on. And we can even make all kinds of nanochannel geometries. Here you could have a dead-end side channel where the interface between the two liquids will end up stabilizing, and you can image reactions going on in it if you want to. If you want to control reactions, another way we're doing it is to use nice little side channels to our main nanochannel. So for instance, if you want to see a precipitation reaction, take some calcium ions and some carbonate ions, and you'll form calcium carbonate, which is a typical test reaction, you could say, for liquid phase TEM. And if we flow in first a calcium precursor, it'll fill out all the reservoirs. And then if we flow in a carbonate reagent into it, there'll be diffusive intermixing between the two. But if we flush real fast in the main nanochannel, it won't really mix very much, and there'll be very little precipitation in the main channel. But out here in our side channels and with the reservoirs, there's plenty of time to make a reaction going and diffusive mixing of the two. And what we'll see here is that the bottlenecks will be filled with calcium carbonate precipitates. So with these nanochannels, now we can begin to control diffusion, mixing, and flow in the field of view, which is not really possible with the commercially available systems. And if once you've formed a reagent by flushing in a reagent 2, if you keep on flushing reagent 2, well, I mean, then that's not saturated with calcium carbonate. And if you got a carbonate crystal here, it'll start dissolving and it'll saturate the solution flowing down. So you will start beginning seeing dissolution processes, but in a very controlled dissolution front moving down through the channel. It's quite beautiful, I think. Another fun little thing you can see here is there's lots of particles. And out here, you can actually get a third-dimensional view of the thickness of the particles. So from these nanochannels, you can get a better three-dimensional view of what's actually going on in your channels and what's the thickness of the layers you're forming. So it's altogether a really nice system for studying precipitation and dissolution reactions. And when I look at all this, then it's a little like I need to read the book on nano and microfluidics. I definitely need to read the book on transmission electron microscopy. There's so many different ways we can see what's going on with the nanoscale fluidic phenomena. And then, of course, we could take like the Handbook of Nanotechnology and say there's so many fun physical, chemical, and biological processes that we could start looking at. And in a way, these three books give you the operational space for this system. And if I make it in 3 dimensions, well, my little research group can only do so much of this vast space of possibilities. So some years ago, I thought maybe we should be more than just me working on the nanochannels. And we formed a company with Emil, who was doing his master's project in the group back then, but he's now the CEO of a nicely growing startup company. And in the company inside chips, we make the chips with the nanochannels. We make systems you can fit into an SEM or in an optical system. And then we also make TM holders for all types of TMs. So if you want to try out the chips, you can contact me or Emil. I mean, if it's commercial and you just want to buy it, it's Emil and you can get a quote on the price. But if you want to do research collaboration, you contact me, and we're very open to do collaboration because, I mean, there are so many things that we would like to do with the nanochannels, but only so much that we can do. And if we zoom into a chip, I mean, you can make all kinds of fun geometries here. So if you want Mickey Mouse shapes, we can give you Mickey Mouse shapes, but this is kind of a library of fun little geometries. We can make straight channels with flow. We can make conical channels where you change flow velocity as function of position. We can make dead ends where it's only diffusion that goes in there. We can make reservoirs in them. That reservoirs that work as pressure sensors and bulge out when you pressurize them, or reservoirs that don't bulge out. You can make huge channels that have a fraction of the flow that goes through the microchannels, and then all types of fun mixing geometries and combinations of different geometries. So there really is a huge space of fun new possibilities to do nanofluidics in the TEM with this system. So from the actual chip system too, let's try and use them for something. Here is one thing we're working on right now, and that's called electron diffraction. Now, that's in a way nothing new, but there is a science paper from a few years ago where there was a big quote in the middle of it saying, why didn't we think of this earlier? And the whole point being that electron diffraction has been there for about 100 years. But what's now called 3D electron diffraction or serial electron diffraction, where you tilt your sample and slowly do a series of diffraction images, is really nice for characterizing extremely small crystals. And where do you find really small crystals that are very complex? Well, typically in pharmacy. And pharmaceutical compounds are small organic compounds. They very often crystallize out. And when they form a crystal, they typically can form many different crystals forms called polymorphs. And it actually turns out that very often the active component of a pharmaceutical compound is just one or two of many possible polymorphs. So pharmaceutical companies are really, and scientists are really interested in knowing population statistics of crystals in their compounds. And that's actually really difficult because the crystals are typically very small. And if you want to study the crystal by diffraction and get the crystal structure, you can do neutron diffraction, but you need large millimeter-sized crystals. So you can do X-ray diffraction, and you can do it in a synchrotron. It gets very expensive, but then you can begin to study small crystals. But electron diffraction actually is really nice for just that type of crystals that is often the bottleneck in pharmaceuticals. So here we have a nice application for it. And typically it's done in cryogenic TEM. But now we can take a nanochannel filled with a relevant liquid, be it blood or salvia or just water or electrolyte at a given temperature, and have our little nanocrystals in and flow it by. We can tilt them in the microscope and get a diffraction pattern while tilting. And from this, then we can start reconstructing 3-dimensional structures. And Xiaodong's group at Stockholm University is one of the world leading groups in this, and we're making a really good collaboration with them. And our first test of this was just to try to see if we could find the crystal structures of glycine. Glycine is a simple amino acid, nothing fancy there, but it forms alpha and beta glycine. And what we can see, if we precipitate out glycine crystals in the nanochannels, then actually when we are imaging, we can both find alpha and beta glycine as expected. So that's really nice. In our current system, we're a little limited in the tilt angles we can achieve. And from that, sometimes our structure of the actual molecule we see in here is a little distorted. But it's really nice to see that we can now, in a liquid, in a TEM, begin to make molecular resolved structures of crystals and also find the crystal structure of small crystals. So this is something we expect we'll see a lot more of in the coming years. And there are several companies now beginning to make electron diffraction systems, and hopefully they'll eventually adopt into using nanochannels as well, to not just look at dry or cryogenic samples, but also to look at samples in liquids. So that's one application you could say that has some maybe bigger relevance out in the real world. Then there's something we pursue a lot in my group, but we're kind of the only persons doing that, and that's trying to combine the liquids with what's called electron holography. Now, electron holography is an interesting method because it allows you to measure electrical potentials inside your sample in a TEM, but it's a little complicated, and I'll tell you a little more about it now. The overall aim of what we're doing here is to hopefully be able to directly image the driving force of a process on the nanoscale instead of just looking at the effect of it. Would we be able to observe and map out the potential that's driving the formation of a dendrite that's growing, or a crystal forming in one way or another, or maybe electrophoretic motions of particles and so on? So this is the overall underlying scope of what we're doing. How we're doing it by holography is to use the fact that in an electron microscope, when you have a good one, you have a fairly you have a monochromatic beam, and it's also coherent, so we can form really nice interference patterns. So if we take a part of our electron beam and pass it outside our sample, it'll be an unperturbed wave passing down to our camera, and the other part of the beam we pass through a sample, and then it'll go through the sample and have a different wavelength and have a different phase as it comes out. So there will be a phase change down on our camera between these two. The phase change, it turns out here, is given by the integral of the electrical potential that the electrons experienced as they pass through the microscope, if we ignore magnetic fields here. And if it's just, one potential, say in a block of ice or water or metal, a simple material, then it's the average potential you experience in the material, called the mean inner potential, and the thickness of it. And that mean inner potential, it's actually a material constant, a little like density or stiffness or Young's modulus, but it's just a material constant that very few people are actually interested in, unless you do electron holography, and very few people do it. So there's not really much mapped out in this. So we need first, before we start working in liquids, we need to start knowing the mean inner potential of liquid water. And another thing, once you start applying different potentials, it's simply the overall potential, and then they'll be added to the mean inner potential. So if we know the mean inner potential, now we can begin to map out the bias potential through the phase change that we're actually observing. Now, the phase change we observe by making an interference pattern of our unperturbed beam and our perturbed beam on our detector. And then from that image, with a little mathematics, we can recreate a phase image so that each pixel tells us the phase change we had in that position. And that phase image then gives our potentials through this integral. And first of all, we need to know that mean inner potential. So what we did was we took a nanochannel, filled it with some water. This is a cross-sectional view. There was a bubble in it as well. And that's nice because then we can, here in our phase image, have the membrane outside the channel. We have the side wall of the channel, the water, and the bubble. And we can see in the water region, we get a very nice phase change. And we also here in the bubble region get a signal that's very similar to what we had outside on the completely dry membrane. And when we do this for different channels with different heights, we begin now to map out the dependence on phase shift with liquid thickness, and that gives us that mean inner potential of water, and that we measured to be 4.5 volts roughly. So you can consider this as a kind of refractive index for electrons in water. It's not a potential that would do electrochemistry or anything. It's for high energy electrons passing through the water. And one nice feature of this was there was only one value of this mean inner potential back from 98 done on vitrified ice. And it was very uncertain. And our value is somewhat higher and with much better uncertainty. And when we talked to some experts, Sean Kathman at PNNL, we could compare this to the best quantum mechanical models of water today. And it turned out that if you put all the bells and whistles in those models together, you can actually get a matching value from our experiment to the theory of quantum mechanical models of water. So our experimental value is becoming kind of a benchmark for people doing quantum mechanical models of water. And it's also nice to see that it's just below what's called the independent atomic model, which sets an upper theoretical limit of the value we should get. So not only do we do something that we can now use for holography, but it's also helping theoreticians modeling lots of other systems where you have electron emission from water. Now, I mean, I tell you, this mean inner potential is a little like a refractive index. And then you could, of course, go back to a chemical lab and say, hey, what do we use refractive indices for? And one of the things, if you've done chemical synthesis, is you would often try to measure the optical refractive index of the solution of whatever you were synthesizing. And from that, estimate if you had done a correct synthesis. You can also do it to measure out concentration of alcohol or sugar in water and things like that. So optical refractometers are nice. And what we've done here is now to try to see if we could make a TEM-based holographic electron refractometer. So we took different mixtures of water and glycerol that has a very high mean inner potential. And here we can see the red dots are our theoretical upper limit for such mixtures, and the black ones are our measurements of the measured mean inner potential that we see here. So we can see we can now make now it's actually a mapping refractometer because this is based on imaging. So we can now begin to quantify, in this case, hydration levels of glycerol and water on the nanoscale if we wanted to. So this is something we hope will help making very quantitative TEM images of structures. Of course, it's a little more involved than just taking a standard TEM because you need to be able to do holography in it, and not all TEMs can do that. And let's try to put a sample into our liquid now and see what we can see there. So here we put a gold particle coated in a polymer shell. So this is kind of a model system for lots of nanomedicine structures, you could say. And then we pass the reference wave through the liquid and the object wave through the particle to get the image. And if we plot what we see here radially from the center of the particle, then we see a huge phase change due to the gold. And from this, we measure the mean inner potential of gold to be about 21 volts, which is nicely in agreement with what you find in literature. There's huge variation what people find there, but we're kind of nicely close to what's there. And also we can begin to now map out the phase change that the electrons experience in this polymer shell. And from the polymer shell, we can also begin to estimate, because if we know the unhydrated solid polymer mean inner potential, and that we can calculate theoretically, then we can begin to predict how much water is actually in here. And from these measurements, we probably would say we got about 30% water in here. So now we can begin to do quantitative measurements on complex nanostructures in liquids and map out potentials. Right now, you could say with some uncertainty, because I mean, it's plus minus, half a volt. An electrochemist, they would probably rather have, say, plus minus 50 millivolts. So the uncertainty on this absolute scale is not so nice. But these measurements we can do now also make it possible to measure hydration levels. And I can tell you a lot of people doing nanomedicine or other things would really like to know those get them quantitatively out. But let's go a little more into the actual potential maps then. So we take our phase change, we measure it, and it's the combination of all the potential measured, and we have the mean inner potential, which is the potential from the core of the atoms and molecules in there, and then we have the bias potential that's also coming in here as well. If I put 0 bias potentials on an electrode, for instance, so it's at 0 and this is 0, then it's just the mean inner potential contribution I would have in my phase change. And if I save that image and then apply a bias, then I'll get an added value just from that. And if I subtract my initial 0-volt image, then I get the actual contribution from my bias voltage. So if I use the 0-volt bias as a reference image, I subtract, then I can now begin to get a map of my actual bias potential in my sample. This we think is pretty sweet. Hey, could we begin to map out potentials applied in electrochemical systems? Now, yep, come along. That's, of course, what we are trying to aim at here, looking at a driving force of a process instead of just the effect of it. But we are facing a little issue here, and it's 100 years old because Gibbs and Guggenheim and more recent papers cite these old gentlemen. And Gibbs back there 100 years ago said that, the electrical potential difference between 2 points in different medium can never be measured and has not yet been defined in terms of physical realities. It is therefore a conception which has no physical significance. Now, that's a pretty hard statement, I should say, and now we're just trying to go ahead and do something without ignoring Gibbs and just do what we want to do. So let's see what we do. We take a clamp chip system that we built ourselves. It's got electrodes in there, bulging liquids, but if we apply a vacuum to the water and squeeze it well, we can actually get very thin membranes here with nice electrodes. And in the TEM, we can go in and find regions where we have extremely thin liquid, and we're actually able there to do holography. Holography requires extremely thin samples to succeed and have a nice coherent beam passing through it. Of course, it will be much easier to do it in our nanochannel systems, and we're working on that. And here's how it looks. First, we have our object beam. We pass it through an electrode and the water. The thing Gibbs didn't like, have a solid material and a liquid and try to observe potential differences between the two, and a reference beam further out in the liquid where we expect no serious change in potentials. And then we make a hologram by the two, and if it's in the dry state, we get some really nice phase changes as functions of distance from the electrode. And we've done extensive COMSOL modeling of the entire electrical fields out in 3-dimensional space to make sure we account for all possible 3-dimensional fields that the electrons will sense in their pathway. And we can make our 3-dimensional model match almost perfectly with our experiments. Then we add the water and flow it in, bang, and something happens here. Of course, water has a different mean inner potential. There's going to be a phase change, but that is subtracted away when we subtract this 0-volt bias. And what we see now is a big change in the way that the potential, or rather the phase change, of course, is away from the electrodes. So there's a huge change in our phase change and hence in our potential. So you could say, oh, wow, you think this is a decaying potential. It looks like it's a double layer, screening of a charged electrode into an electrolyte. So it looks compelling. But let's do our full 3-dimensional modeling of this. And what we've done here is to take our low voltage signal, because that's where our models work well, but that's also the noisy signal. And then we are taking COMSOL and trying to model with different electrolyte concentrations to see where it actually is. And the actual electrolyte concentration we used here was very low and suggests a much lower screening than what we observed. The potential drops off much faster in the liquid. Actually, we need to account for maybe 10 millimolars of electrolyte to begin to have a nice match between our experiment and our model. But then again, extremely dilute electrolytes in a clamp chipped system here is in a system that's very dominated, first of all, by surfaces that could be slightly dirty, but also we didn't degas the water we were using here. So there's carbon dioxide and other gases present that will increase the conductivity. So it is not unreasonable to think that we are of the order a few millimolar of electrolyte. So I think here we can say that we are into something that looks sensible, and we're getting closer to something that could be a first image of screening of an electrode in liquid, and maybe also challenging a little our old friend Gibbs and what's actually possible in terms of imaging and measuring. Of course, there are many other effects we need to start looking into, such as electrokinetic effects, if our membranes charge up and attract ionic species and so on. And if we go a little back to Gibbs, I mean, one thing we could start discussing here is what potential is it really we're talking about? And there are quite a lot. I mean, what we are mapping out is the electrostatic potential, and we can model it in our three-dimensional model. So this is the physicist's electrostatic potential. But when the physicists meet the chemist, well, then the chemist will say, well, look, you come here and talk about a mean in a potential. That's one. But the electrochemist will talk about a whole lot of different potentials. I just listed all the different potentials I could think of, and there are many. Some of these are actually the same potential, just with different names, and some of them are combinations of others. And there is a nice paper called Potentially Confusing Potentials in Electrochemistry, and I agree, there are a lot of potentials. So even if I, as a physicist, come and say, hey, I measured the potential, the chemist will say, which potential is it, and did you account for the surface potential? Or, could you be influenced by other aspects here? Because there are many things going on in liquids. This is something we're trying to unravel now. And it's also what links back to Gibbs' problem, because Gibbs was back then thinking of the aspect of taking a physical probe, dipping it into a liquid, or touching it onto a piece of metal. And when you take a physical probe and touch a piece of metal, you can measure the potential on that piece of metal. But once you dip it into a liquid, it'll have a double layer surrounding it, and the actual potential you measure will not be completely representative of the solution potential you have inside it. So I completely understand Gibbs' worry, but our point being here that with an electron beam, we can avoid the double layer from our probe. So if we avoid the physical probes and use the electron beam, if the electron beam does not perturb our system, we can now begin to map out electrostatic driving forces in liquids. So we think we're on our way to that. We can also do it in other systems. And now you were discussing previously things that were dry and hot in an environmental TEM. And we also have one of those here. And one of the things we're trying to do now is to combine work that some people here at D2 Energy is doing on solid oxide electrolyzers. Those are ceramic systems, very complex ones with different electrodes and electrolytes made from ceramics that work in gases at several hundred degrees, such as oxygen atmospheres. And then we're trying to start beginning mapping out potentials with electron holography in such devices to give them a potential measurement of the device, which is really complex. I mean, they cannot get it in any other way. So hopefully that's something you'll hear more about. It's ongoing work here. And then from that kind of dry state, we'll go to another more exotic liquid that we're working a lot on. For many years, we've been working on droplets of gold and gold silicon and gold gallium that are sitting on tops of nanowires that are growing inside an environmental TEM. So this is a liquid eutectic mixture of two metals, and it's sitting here at the top of a nanowire that's catalytically growing at, say, 500 or 600 degrees. And these nanowires are quite interesting. They have a lot of possible applications, first of all, for fundamental physics to understand what's going on. There's been several attempts to use them in solar cells and sensors, and recently they're finding a new application in quantum devices because you can make extremely nice quantum dot structures that are optically active and maybe could be used for quantum-based sensors, communication, or computing. And what you do, let's say we want to grow a silicon nanowire, then you'll take a silicon crystal, put a little piece of gold on top of it, say a gold nano particle, you will anneal it to maybe 400 degrees or 600 degrees because it melts already at 360 when it's a gold silicon eutectic, and form a nice interface between a molten eutectic droplet and the silicon. And then you can add a gas. If you want to grow nanowires with silicon, you can add disilane gas and heat up at 500 degrees, and then silicon will precipitate out and grow up a nanowire headed by that catalytic droplet, where the gas is impinging on the droplet, then it's cracking up and forming a molten silicon phase inside the eutectic that then crystallizes out the silicon nanowire. And if you change the gas, put some germanium gas in or something else, then you can make parts of the nanowire of different materials. And in this way, you can grow quantum dots on a line, and you can do it quite controlled. And you could say that today the toolbox you have for nanowire growth is you can control the position of the gold by lithography. You can control the direction of the growth by controlling the substrate. It grows typically in the 1-1-1 direction. That means you have direction control. The particle size gives you the diameter. The length you control by time and pressure and temperature. And if you want, you can change to different gas mixtures and change the composition of the wire. So this is a really nice mechanical toolbox, you could say. And I worked for many years with Frances Ross at IBM, and she's now a professor at MIT doing lots of nanowire studies. And what we did was, instead of just heating some substrate up in a TEM, we created a unique microchip system with crystalline cantilevers that we pass a current through to make them hot. And then we put the crystal orientation so that the 1-1-1 direction is perpendicular to the electron beam. And that means now we can start growing nanowires from one heater to another. And then the nanowire can reach the other wire, and we can then make electrical measurements on it, or we can perturb the growth with electrical fields, or we can do fun experiments on the nanowire once it's connected. You can, for instance, if you have even potential, see how the droplet wets the opposing cantilever and then grows a solid connection of silicon between the two cantilevers. Or we can start applying a current and migrate the gold away and change geometries of the contact point. There's so many fun things you could do in this system. And another thing, just before contacting the opposing cantilever, you can apply an electrical field and disturb or perturb the droplet shape. So now we're studying the surface tension of a droplet and the balance of that with the electrical field pulling it from the droplet. And what we can see is, as we apply a potential over time, we will then start seeing, let me just see if we can run it again, then we'll change the aspect ratio of the height versus width of the droplet. And from that relation between potential and aspect ratio, we can compare two models and begin to assess what is the surface tension of that droplet. And that's, of course, a slightly exotic material constant to begin to measure. But if you want to theoretically understand how to grow nanowires, you really want that surface tension, because it's absolutely fundamental to all models of nanowire growth, and it has never been measured. And from this work with Frances and Federico, we measured the surface tension of silicon nanowire gold eutectic and found that value. We're just updating it to a new one. But also then Kimberly at Lund University, Kimberly Talander, got this amazing new, humongous environmental TEM. So in this TEM, we're not able to grow just silicon, but we can grow all kinds of 3-5 semiconducting nanowires. And instead of the old TEM we had at IBM that had very poor resolution, now we get atomic resolution, and we can see atomic layer by layer as the nanowires are growing in the TEM. And with our chip systems, we can begin to deform the nanowire droplet and see how that influences the nanowire growth. So this gives us a completely new set of glasses to much better see what's going on. And Christopher Røhl Andersen just finished his PhD on this. And one of the things we focused on doing here was to try to engineer crystal phase quantum dots. And the idea here is that if we can make a phase change between two crystal structures, then we can also create a quantum dot. So Nika Kopian from DTU back in 2010 proposed that if you in nanowires, you can have two types of crystal forms of, say, gallium arsenide. In a bulk crystal, you can only have one, but in nanowires, you can actually grow two different types of crystals. And if you shift between these two crystals, you can create regions with a different band gap than the rest of the nanowire. That means if you shine a laser on it, the laser will only interact or can be tuned to only interact with a specific part of the nanowire. And because it's a crystal phase change, it's got atomically sharp interfaces. So this makes it possible to make extremely small quantum dots and extremely well-controlled quantum dots that are not really possible today. So in the old days, you would make quantum dots, say, by changing from gallium arsenide to indium arsenide, and that means changing gases, and that takes time to change, and then you will grow a boundary that's very extensive, and you've got a diffuse boundary. But with a phase change, you can make sharp boundaries. And traditionally, you would also do that in a big reactor if you're working on a full wafer by just changing your flow, for instance, how much arsen gas you're flowing in for gallium arsenide, or you would change the heat or temperature. But both of these are fairly slow, so that makes it hard to change it quickly and make good control. On our microheaters, we can change temperature extremely fast. We can change 100 degrees in a few milliseconds. Here's a video of the phase of the temperature change. There's a slight thermal drift as we change from 400 degrees to 500 degrees. And in one frame, you can see it shifts clearly from one position to another. So within milliseconds, we change temperature 100 degrees. And now we can begin to change the temperature as we want. And see here how we change between two different crystal phases, because they are nicely distinguishable, as I showed you in the previous slide here. Actually, you can easily see the difference between the zinc blende and the wurtzite, because they look different in the TEM. And then we can begin to now quantum dots. What is going on here? Sorry. Yeah, here we are. Just a little pop-out on my screen. Now we can begin to engineer quantum dots while we're looking at them growing in the TEM. Another thing, of course, we could do was to start changing the surface tension, or measure the surface tension of this system by applying potentials to distort the droplet. And as we plot the aspect ratio we measure as function of corrected bias and compare it to fairly complex 3D modeling of this system, then we can now begin to measure the surface tension of this droplet, which is then now making it possible to assess which type of models are actually the right ones for surface tension of these complex exotic molten metals. And if you look in literature, there are different ways people try to calculate it, and we're clearly in agreement with one type of model, while the other model is clearly not matching our expectations, meaning the publications using that model are probably not going to be correct. So basically, with this chip system, we can now make a whole new set of control tools for nanowire growth. We can change the contact geometry by putting bias voltages as we hit in and hit the opposing cantilever. We can terminate growth in different ways. We can modulate the diameter by putting fields on it. We can even change the direction by putting fields on it. And now we can also begin to change the crystal phase by changing temperature on the chips real fast. So that was a little venture into some very exotic liquids and nanofluidics, you could say. If you want to see more, you're welcome to come by. One thing you can come by here is to join us in Copenhagen in August. There's a nice session nice conference called the European Microscopy Conference. And we're still open for abstracts. So you can submit an abstract a few days still. And overall, I could say now that I've taken through a tour of nanofluidic TEM, where we now begin to have much more control over flow and conditions than what you have available in the commercially available systems today. And I've shown you that we make these nanochannel chips. Here's my cursor. We can get atomic level resolution in them. We can flow and mix in reagents in different ways. We can get molecular structures by electron diffraction. We can begin to quantify hydration levels and measure this mean inner potential. We can image potentials. I didn't have time to talk about electrokinetics, but that's another new thing we're looking into. And I've shown you some of the results we made on exotic liquids for quantum structures at high temperatures. So I think this these microchips for microscopy are really fun systems that allows you to do all kinds of new interesting things. And you're most welcome to contact me if you want to try them out one way or another, or work with us on it. Thank you very much.